Jupiter is about to gain a new moon, and it should not exist. Out in the darkness, an object called 3I Atlas is threading its way through the solar system with the accuracy of a guided spacecraft, not a wandering chunk of ice and rock. Its path is locked onto a gravitational sweet spot around Jupiter, as if it knows exactly where it wants to park. The math behind that path makes astronomers uneasy. We are going to dig into why this visitor may be far more than a simple comet and what that might mean for us. If you enjoy exploring mysteries like this, tap like, subscribe, and stay with me as we follow it toward Jupiter. You might imagine that what keeps astronomers up at night is the big, loud stuff. Killer asteroids, exploding stars, the fact that most of the universe is made of something we cannot see. Those things are worrying, sure, but they are at least chaotic in a way we understand. The real chill comes from something else. Precision where there should be none. A rock that behaves like a spacecraft. A visitor from interstellar space that moves with the discipline of a mission plan instead of the sloppiness of nature. 3I Atlas sits right in that unsettling category. When it was first spotted in 2024, 3I Atlas looked like a familiar story. A faint, fast-moving point of light sweeping in from outside the solar system. A little ice. A little rock. A body probably wandering for millions of years before chance nudged it toward our star. Astronomers logged its position. They worked out a rough orbit. The expectation was simple. It would dive past the sun, flare briefly as its ices boiled away, then swing back out into the dark, never to return. Another cosmic tourist. Interesting, but routine. Then someone pushed the models further. Not just where did it come from, but where exactly is it going? That is where the comfort ended. The refined orbit did not show a random exit into interstellar space. It did not show a casual brush past Jupiter or Saturn. Instead, the numbers locked onto one very specific destination in three-dimensional space. A thin, invisible boundary wrapped around Jupiter known as the Hill radius. 3I Atlas was not simply drifting through our planetary neighborhood. It was homing in on the edge of Jupiter's private gravity bubble. Hill radius sounds like jargon, but the idea is simple. Picture the solar system as a tug-of-war between the sun and its planets. Most of the time, the sun wins. Its gravity dominates almost everywhere. Yet around a giant world like Jupiter, there is a region where the planet's pull beats the sun's pull for anything nearby. Inside that region, Jupiter acts like the boss, setting the rules for orbits. That region is the Hill radius. It is the zone where natural moons can form and long-term satellites can park without constantly fighting solar gravity. For Jupiter, this invisible bubble is huge. It stretches roughly 53 million kilometers from the planet's center. That is a territory on the scale of an entire inner orbit, comparable to the path Mercury traces around the Sunday. Now here is the part that made astronomers stop and check their work again and again. The projected intercept point for 3I Atlas is not just somewhere inside that bubble. The calculations say it will cross the boundary at about 53.445 million kilometers, with an uncertainty of only about 60,000 kilometers. On human scales, that is a rounding error. On cosmic scales, it is terrifyingly sharp. To feel how sharp that really is, imagine you stand in New York and throw a dart toward Los Angeles. You and the dartboard are both moving across the continent. Winds are shifting. The ground is rotating with the Earth. You throw the dart years in advance. Somehow it still lands in the bullseye, not just roughly on the board, but inside a ring only a few millimeters wide. That is the kind of precision we are talking about. Nature can line things up in surprising ways, but this is not a near miss. This is threading a needle over hundreds of millions of kilometers. There is an important difference between a close pass and a target. Space is full of rocks that happen to wander near planets. Every year, Jupiter's gravity scoops up comets and asteroids that blunder into its path, many of them captured into messy, looping orbits, or simply flung away like cosmic shrapnel. Those trajectories look noisy. Their closest approaches have wide margins. Nobody would call them intentional. What we see with 3I Atlas is different. The path hugs a corridor. that leads straight to the hill radius, with an error bar small enough that it feels less like an accident and more like a shot lined up in advance. If you work at a space agency, this kind of number is your daily bread. Mission planners spend years computing exactly how to drop a probe into orbit around a planet without wasting fuel. They tweak the launch window, they adjust the trajectory, they aim for specific gravitational boundaries, because those are the places where a little change in velocity produces a big change in outcome. A natural comet might wander near that sweet spot. A designed spacecraft aims right for it. 3. Atlas is behaving, mathematically, as if someone chose that parking zone on purpose. Officially, in the databases of NASA and the big observatories, 3 Atlas still wears a safe, bureaucratic label. Interstellar Comet. Interesting, but nothing that requires emergency protocols. At conferences and in quiet emails, though, the story is not so simple. A growing group of researchers, including Avi Loeb and colleagues at Harvard, look at the same trajectory and see something that feels less like a fluke and more like an insertion maneuver. In other words, the sort of approach you would design if you wanted to leave something sitting comfortably in Jupiter's gravitational territory for a very long time. Right now, all of that is still an argument played out in equations and probability curves. Maybe this really is the luckiest comet path we have ever measured. Maybe subtle jets of gas from its surface have nudged it, step by step, into this uncanny alignment without any guiding mind behind it. Or maybe the precision is trying to tell us something. The scary part is that the trajectory is only half the story, because there was a moment when 3 Atlas slid behind the sun and our instruments went partially blind, that something else seems to have happened to its path. And the closer you look at that missing window, the stranger this new moon begins to seem. Every orbit we calculate begins with a simple assumption. Space is predictable, gravity is steady. If you know where something is and how fast it is moving, you can project where it will go. That quiet confidence breaks down in one place. When the sun steps between us and our target, we go half blind. That is exactly what happened with 3 Atlas, right when it was whipping around the sun, right when any subtle change in its path would matter most. Our view cut out, and when it came back into sight, it was not quite where it should have been. Astronomers have a name for this situation: solar conjunction. It sounds gentle, almost musical, but for tracking, it is a nightmare. Take Earth, the sun, and your target, and line them up so the sun sits in the middle. The sun's glare floods every detector pointed in that direction. Optical telescopes see only blinding light. Radio signals drown in a sea of solar noise. For a while, you simply cannot take precise measurements of anything lurking close to that line of sight. The universe does not pause for you. Your target keeps moving, and you are forced to coast on your last good data. For 3 Atlas, that blackout window lasted on the order of a couple of days, 40 to 60 hours, where the object was too close to the sun on our sky for reliable tracking. Observatories around the world handed the problem off to computers, propagating the last measured orbit forward in time. The models drew a smooth curve around the sun and out the other side, predicting where the comet should reappear once the glare eased. Then everyone waited for the tiny point of light to come back into view. When it did, something was off. Not dramatically. 3. Atlas was not in a wildly different place. It had not suddenly veered toward Earth or crashed into the Sunday. The difference was subtle, just enough to show up when you compared prediction to reality with fine tools. Its speed had increased by a small amount. Its direction had shifted by a small amount. Together, those changes nudged it onto a slightly different track. The new track did something important. It tightened the aim toward Jupiter's hill radius. In the language of orbital mechanics, this is called non-gravitational acceleration. Gravity is not enough to explain the change. Something else pushed. For comets, there is a standard, well-tested culprit: outgassing. As a comet nears the sun, its ices heat up and turn directly into gas. That gas vents from cracks and pits on the surface, acting like tiny thrusters. Each jet pushes a little, Over time, many random pushes can add up to a noticeable drift in speed and direction. We have watched this happen in dozens of solar system comets. It is normal. At first, that is exactly how the story around 3I Atlas was framed. It hit perihelion, the closest point to the Sun, during conjunction. It heated up, it vented gas. The resulting jets gave it a small kick, just strong enough to show up in the numbers. Case closed. The fact that we missed the exact moment of the event was just bad luck. The timing fit the simple picture beautifully. Closest approach to the Sun is when comets are most active. Closest approach to the Sun is also when the Sun blocks our view. Physics and geometry line up. But then people started asking harder questions. The first was about direction. If outgassing is a wild, chaotic thing, why did the push line up so perfectly with the one direction that matters most for hitting the hill radius? When you map the change in velocity as a little arrow in space, that arrow points almost exactly along the path needed to refine the intercept with Jupiter's gravity bubble. Not roughly, not within some huge cone of possibility, remarkably close. That is like lighting off a random firework and having it gently nudge a satellite into a cleaner orbit by accident. The second question was about behavior. Real comets often look messy near perihelion. Their comas grow lopsided. Bright jets stream away from localized vents on the surface. The tail can kink and flicker as rotation brings different active regions into sunlight. 3I Atlas, by contrast, has looked strangely well behaved. Its coma appears more symmetrical than you would expect for an object supposedly getting kicked around by violent jets of gas. There are no strong, isolated jets anyone can point to as the source of a big directional push. It holds together too neatly for something in the middle of a powerful outburst. Defenders of the natural view are not being lazy. They point out that if the internal ice is arranged in a very specific way, you can get a more directional thrust. If volatile material happens to be concentrated on one side, and if the object rotates slowly, you might end up with a net push that is biased in one direction over many hours. Given enough weirdness in the composition and shape, you can imagine outgassing that looks surprisingly tidy. The universe allows rare coincidences. We see them all the time in other contexts, yet the coincidences here keep stacking. The magnitude of the push is just enough to slide 3I Atlas into an even narrower corridor toward the hill radius. The direction of the push lines up almost exactly with what a mission planner would choose for a mid-course correction, and the visible signs of wild outgassing are oddly muted. All of them together begin to feel less like random noise and more like a pattern. Now imagine an alternative story that uses the same physics but changes the intent. You design a probe that carries its own propulsion, but you want that propulsion to look natural to any curious observers. You choose a system that vents gas in a way that mimics a comet's sublimation. You time your course correction for perihelion, when solar heating gives you plenty of energy. You fire your thrusters while you are behind the Sun from Earth's perspective, inside the natural blind spot of conjunction. When you reappear, anyone watching can label the shift as outgassing and move on. It is camouflage written in orbital mechanics. We have no smoking gun that proves this is what happened. If 3I Atlas did execute a hit and burn during conjunction, then the path it follows now is not just the result of ancient chance. It is the outcome of a plan, one that aims straight for Jupiter's gravitational harbor. And if this was a plan, the next disturbing question is obvious. Why did that plan treat Earth like an irrelevant roadside sign on the way to a far more important destination? If 3I Atlas is following a mission plan, Earth has already been judged and dismissed. That sounds dramatic, but look at its behavior. On the way in, it passed through a distance where any capable probe could have learned an incredible amount about our planet and our technology. The kind of flyby our own space agencies would dream of if we were spying on another civilization. And yet, in every dataset we have, we see the same thing. Nothing. No slowing. No turning. No sign that we were even worth a glance. During that Earth encounter, astronomers watched closely for any hint of curiosity, a change in brightness that might mean the object rotated to point sensors at us, a tiny tweak in velocity, like tapping the brakes to take a better look. Maybe a brief spike in thermal emission as instruments warmed up for a scan. Instead, the record is boring in the most unsettling way. 3I Atlas held its course, held its speed, and sailed past like we were just another faint signal in the background. Think about how we behave when we send probes through the solar system. Passing near a world is a precious opportunity. Voyager swung by Jupiter, Saturn, Uranus, and Neptune, and at every encounter it twisted, aimed its cameras, burned fuel, and grabbed every scrap of data it could. New Horizons did the same at Pluto. These flybys were the entire point of the mission. You do not waste a close pass. Not if you care about what you are passing. So what does it mean when something does waste it, at least from our point of view? Imagine you are driving down a highway at night. Ahead is a small exit for a town you have never heard of. You do not slow down. You do not even really look. Your destination is hundreds of kilometers away. A city you chose long before you started the engine. That is how 3I Atlas treated Earth. Just an unnoticed exit sign on the way to somewhere that actually matters to it. This is where the story stops being about us and starts being about Jupiter. Because if Earth is not the main event, then the only reason to accept the risk and effort of entering our solar system is something bigger and more strategic. Jupiter is not a cozy world in the habitable zone. It is a monster of gravity and magnetism, a failed star wrapped in dense cloud and deadly radiation. To biology like ours, it is a nightmare. To machines, it is prime real estate. Jupiter's gravity is a builder of systems. It shapes asteroid belts. It shepherds Trojans. It constantly captures and tosses smaller bodies, rearranging the outer solar system with every encounter. Anything that learns to sit comfortably inside its hill radius gains access to a powerful anchor point. You can park for ages with minimal effort. You can slingshot to other destinations. You can use Jupiter as a kind of gravitational hub for moving hardware around the system. If you are planning infrastructure rather than a quick visit, that is where you go. Then there is the magnetosphere, Jupiter's vast bubble of magnetic field and charged particles. It is the largest coherent structure in the solar system, after the heliosphere itself. If you could see radio waves with your eyes, Jupiter would look like a blazing lantern wrapped in a huge invisible storm. For electronics designed to harvest electromagnetic energy, this is a natural power plant. No need for giant solar panels. No need for nuclear reactors. Just dip your systems into the particle flux and drink from it indefinitely. From a surveillance perspective, the view from there is almost unfair. Sitting out near Jupiter, you are far enough away to watch the inner planets sweep around the sun like hands on a clock face. Earth glows in radio and thermal wavelengths, a noisy little world wrapped in an artificial shell of transmissions and satellites. Mars, Venus, and Mercury all trace their own tracks. A network of quiet observers in the hill radius could keep continuous watch on all of it, logging every rocket launch, every burst of radar, every new spacecraft leaving low Earth orbit. The beauty of this position, if you are trying not to be disturbed, is that it is inhospitable to curious life. We send probes to Jupiter, yes, but we treat its inner magnetosphere with caution. The radiation bath near Jupiter can fry unshielded electronics in hours. For organic bodies, it is lethal. That means any hardware tucked into the more extreme parts of that environment is naturally shielded from casual visitors like us. We do not have the technology or the appetite yet to go poking around deep inside that storm for hidden machines. Seen through that lens, the indifference to Earth starts to make a cold kind of sense. If your goal is to build a long-term observation post, you do not risk revealing yourself with dramatic maneuvers near a noisy young civilization. You go where the physics is most helpful and the locals are least likely to interfere. In this case, the high ground is a region of space tens of millions of kilometers wide, wrapped around a gas giant that we can barely approach and barely see into. Of course, there is another possibility, one that is both humbling and a little painful. Maybe we are simply not interesting enough yet. In our own history, Explorers often sailed past isolated villages and small islands without stopping, focused on larger harbors or more valuable resources. The people living there might have watched ships on the horizon and wondered what they meant, never realizing they were not the main characters in the story. 3i Atlas could be replaying that pattern at a cosmic scale, heading for a port it planned centuries or millennia ago, while we stand on the metaphorical shore and watch it go by. That is the psychological sting at the heart of this object. If it is natural, then fine. We are watching a strange comet follow a surprisingly lucky path, and the story is about physics and probability. But if it is not natural, if the precision and the indifference are both signs of intention, then we just learned something uncomfortable about our status in the neighborhood. We are simply being observed from a distance that suits whoever is really making decisions. And that leads to the next, even bigger question. If Jupiter is the place to build an invisible watchtower, what exactly might be waiting to unfold when 3i Atlas finally reaches its mark inside that gravity bubble? Up to now, we have been treating 3i Atlas like a single question. A weird comet. A possible probe. One object with one story. That might be the wrong scale to think on. There is a different way to imagine what is happening, one that shifts the focus away from the traveler and onto the destination. In that picture, Jupiter's hill radius is not the endpoint of a strange orbit. It is a construction site. And 3i Atlas is not the star of the show. It is just the delivery truck. Engineers have a ruthless way of thinking about problems. They care about efficiency, about what lasts. If you wanted to explore a galaxy filled with hundreds of billions of stars, you would not send heroic crews on giant ships to each one. You would send machines. Small, tough, cheap. Multiply them by a huge number and give them a simple job. Go there. Set up eyes and ears. Watch. Report. That idea is often called sentinel theory. Star systems are not visited by people. They are seeded with networks. In sentinel theory, the real magic is not in the individual probe. It is in where and how you deploy them. You pick spots where orbital mechanics does the hard work for you. Gravitational harbors where an object can sit for centuries without burning fuel. Around a massive planet like Jupiter, the hill radius is the outer fence of that harbor. Inside it, there are even more precious anchor points that let you park hardware almost for free. These are the Lagrange points, places where the gravity from Jupiter and the gravity from the Sun balance in just the right way. The L1 point sits between Jupiter and the Sunday. An object there hangs in space along the line between them, held in place by a delicate tug of war. From that spot, a sentinel can stare at the Sun, the inner planets, and Jupiter all at once. It has a constant, unbroken view of the action. The L2 point sits the same distance from Jupiter as L1, but on the far side, always hidden in Jupiter's shadow from our perspective. Anything parked at L2 is naturally shielded from sunlight and from direct line of sight with Earth. It is a built-in hiding place. Now imagine a carrier craft that arrives at the edge of the hill radius with a cargo hold full of smaller units. It does not need to be very large. It just has to survive the interstellar cruise and arrive with enough propellant or clever physics to change course a little at the right moments. When it reaches the right region of space, it does something that from a distance looks perfectly ordinary. It fragments. Pieces peel off and drift away. To our telescopes, it is just another comet falling apart under tidal stresses and heating. We have watched that happen many times. Except in this story, the pieces do not behave like random rubble. Some slow down relative to the main body, some speed up a little. Their paths curve toward those Lagrange points, or toward long-term stable orbits that loop around Jupiter in wide, quiet arcs. A few might head inward toward promising moons like Europa or Ganymede. Others might settle into high, inclined paths that give them sweeping views of the whole system. Each one uses minimal fuel, leaning on gravity and clever timing. Within a few months, the sky in Jupiter's neighborhood holds not one object, but dozens, scattered through the gravity bubble like seeds. From Earth, the view would be underwhelming. The fragments are small and dark, Their surfaces are engineered to reflect as little light as possible. We see maybe a handful of points where we once saw one, blinking near the edge of detectability. As time passes, they spread out and fade into background noise. Without dedicated tracking and deep observations, they vanish into the star field. The headline becomes a simple one. Odd comet breaks up near Jupiter. Mystery solved. Meanwhile, from the inside of that network, our solar system now looks very different. At L1, a sentinel watches the inner planets parade around the sun, catching every radio burst, every high-energy flare, every spacecraft launch. At L2, another sits in a permanent eclipse, its instruments cooled by darkness, shielded from our direct line of sight. In high orbits, others scan the outer system, track trans-Neptunian objects, and monitor the big ice giants. Together they form a distributed observatory, with no single point of failure and no need to ever go home. Jupiter's magnetosphere turns this passive watch into something closer to a permanent station. Inside that huge electromagnetic bubble, you can harvest energy simply by moving conductive loops through the charged particle sea, or by exploiting the changing magnetic field. It is the same basic idea as a generator, scaled up to planetary size. For an advanced probe, that energy is almost endless. You can run sensors, repair systems, and communication gear on what Jupiter is already throwing away as radiation. All of this fits uncomfortably well with what we know about long-term engineering. When humans build infrastructure, we look for similar leverage. We tether space stations to the right orbits. We park satellites at our own Lagrange points. We plan around fuel and stability and line of sight. Sentinel theory is simply that way of thinking extended across light years and deep time. Do not visit. Settle. Do not pass by. Embed. Let gravity and magnetism hold your machines in place and let the sky drift past them. The fear, once you see this picture, is not that 3I Atlas will collide with Jupiter or sling something dangerous toward Earth. It is that the truly important part of the mission will be almost invisible from where we sit. A brief fragmentation event that we interpret as natural. A slow, quiet dispersal into orbits we rarely study closely. Then centuries of patient watching from platforms we mistake for rocks or never detect at all. The story stops being about one object and becomes a question about background architecture. Has this already happened elsewhere in our system? Are there other networks roosting in other gravity wells that our instruments are too crude to reveal? 3I Atlas might be the first time we catch a carrier in the act. With our telescopes and our software just good enough to see the precision in its path and ask whether we are really looking at a comet or at logistics. And if it is logistics, then someone, somewhere, is not just visiting, they are moving in. 3I Atlas feels less strange when you pretend it is alone. A one-off curiosity. A freak comet from the deep. The discomfort begins when you remember it is not the first messenger from interstellar space we have seen. It is the third, and when you put all three side by side, something starts to tug at your pattern-seeking brain. Either the universe is playing a very specific joke on us, or we have been watching an unfolding sequence without quite admitting it. The story begins in 2017, when telescopes in Hawaii picked up a speck moving far too fast to be bound to the sunday. It followed a hyperbolic path, came from nowhere we recognized, and carried a name that matched how it felt. Oumuamua, a visitor from far away. As the data came in, it refused to behave like anything familiar. Its brightness flickered in a way that suggested a long, cigar-like or pancake-like shape. Its surface was oddly reflective, and most annoying of all, it sped up as it left the inner solar system without showing the glowing coma of gas that should explain that push. For months, every new paper about Oumuamua looked like a creative writing exercise pinned to equations. Maybe it was a fragment of nitrogen ice shaved off a Pluto-like world. Maybe it was a hydrogen iceberg that evaporated invisibly. Maybe dust. Maybe a frozen fluff of exotic material. None of the natural explanations fit cleanly. They all needed unlikely starting conditions or fine-tuning. That opened the door for a far more uncomfortable proposal. That Oumuamua might be a thin, flat structure pushed by sunlight like a light sail. not proof of technology, just a reminder that technology could fit the data just as well as some of the wilder natural guesses. The community reacted the way a healthy scientific culture should, with skepticism, with arguments, with sharper models. By the time Oumuamua faded beyond our reach, there was no consensus. The object was too small and too fast. The window was too short. It left us with an ache instead of an answer. Then came 2I Borisov in 2019. Where Oumuamua had been elusive and odd, Borisov was a relief. An incoming object whose path said Interstellar, while its appearance said Comet in every language astronomers speak. It grew a tail. It outgassed familiar molecules. Spectra showed water, carbon monoxide, and other ingredients we already knew from homegrown comets. In a way, Borisov became the official reassurance. Interstellar visitors, we could tell ourselves, really are mostly just dirty snowballs flung out of young planetary systems. Oumuamua was the weird one. Borisov was the baseline. That comfort did not last long, because 3I Atlas arrived, carrying traits from both of its predecessors, and then added more unease on top. It looks more like Borisov than Oumuamua in the most basic sense. There is a coma. There is activity. It behaves photometrically like a comet, yet its motion through space is closer to the kind of puzzle Oumuamua posed, non-gravitational accelerations that line up just so. A path that becomes more precise instead of messier after the violent heat of perihelion. If you step back and draw the simplest possible summary, you get this. First visitor, strange shape, no coma, odd acceleration away from the Sunday, in that at Great 9Y, 200. Second visitor, comfortingly normal comet. Third visitor, comet-like appearance plus a disturbingly exact mission profile. You can tell 3 different stories about these 3 objects. In one story, they are all natural, and the weirdness is just our ignorance. In another, only one is artificial, and the others are cosmic background. In a third, they are iterations in a learning process. The first too obvious. The second, a control. The third, a better compromise between hiding and accomplishing a goal. That last story sounds like paranoia, until you remember how we behave with our own technology. The first prototypes are clumsy and easy to spot. Later generations get smaller, cleaner, more subtle. If some distant civilization ran a program of probes visiting many stars, you would expect the same arc. Early attempts might leave exaggerated signatures. Later ones would look more and more like nature, especially if the designers had any reason to worry about being detected. There is another layer to this pattern hunting. Geometry. All 3 interstellar objects we have tracked passed relatively close to the plane of our solar system, the thin disk where the planets orbit. That is good observational bias. We are more likely to detect things that cross that plane, but if probes were being aimed, that is also exactly where you would send them. You want to intersect planets, not waste time far above or below them. Seen from far away, our system is a faint ring. Hitting the ring again and again is the smart way to operate. Skeptics are right to warn about human brains and patterns. We see faces in clouds, shapes in noise. 3 data points is almost nothing in statistics. You could take any 3 random comets and stitch together a story about them if you tried hard enough. That is why most professionals still lean heavily toward natural explanations for all of these objects. The default rule in science is to exhaust the simple options before you reach for extraordinary ones. Yet the specifics of 3I Atlas refuse to fade politely into that comfort. It is one thing to have a slightly odd orbit. It is another to have a path that threads a corridor to a planetary hill radius with the kind of accuracy we associate with human-planned missions. It is one thing to see non-gravitational acceleration in a dirty snowball. It is another to watch that acceleration arrive at just the right time and in just the right direction to refine an already uncanny approach. When you stack that on top of the unresolved questions from Oumuamua and the reassuring normalcy of Borisov, the pattern, real or imagined, keeps resurfacing. Maybe the safest way to phrase it is this: our picture of interstellar visitors is no longer simple. We cannot point to any one of these three and say with full confidence what they truly are. Instead, together, they sketch the outline of a larger unknown. Are we just sampling the wild diversity of natural debris flung between stars? Or are we living in a galaxy where the line between rock and machine, comet and carrier, is blurrier than we ever dreamed? 3I Atlas, on its way to Jupiter's gravity bubble, is about to push that question harder than any object before it. Science always starts with the same bias: nature first. Before you reach for alien probes or cosmic engineering, you ask the boring question: could this just be a strange rock doing strange rock things? 3I Atlas is no exception. On one side of the argument are people saying this is an exotic but still natural interstellar comet. On the other side are those who look at the same data and see something that behaves like a guided machine. The numbers are not arguing. The interpretations are. To understand why the debate is so fierce, we have to walk through what comets actually do. The classic picture is a dirty snowball, a chunk of ice and dust left over from the early days of some planetary system. Out in the cold, it is quiet. As it falls toward a star, its surface warms. Ices turn straight into gas. That gas escapes as jets, pushing off from vents and cracks. Every jet is like a tiny thruster firing. Over many hours and days, those little pushes add up, changing the comet's speed and direction in ways that gravity alone cannot explain. We see this all the time. Solar system comets routinely show non-gravitational accelerations because of outgassing. Their paths wobble just enough that orbital models have to include jet forces to stay accurate. So when 3I Atlas shows a small extra acceleration, the natural explanation is ready and waiting. The sun heated it. The ice vented. The jets nudged it. End of story. That is the simple side of the duel. Look a bit closer though, and the simple story starts to fray. The first problem is direction. Outgassing is usually messy. Imagine steam spraying off a spinning block of ice. As it rotates, different faces are lit. Jets switch on and off. Some point this way, some that way. The net effect is random. You do not get clean, perfectly aligned pushes. You get jitter. This jitter still produces a drift, but the drift is not tailored to hit a particular target with extraordinary accuracy. 3I Atlas, by contrast, seems to have been nudged in almost exactly the direction needed to sharpen its aim at Jupiter's Hill radius. The second problem is appearance. Active comets reveal where their jets are working. You see lopsided comas, bright fans of gas and dust, features that swirl and change as the nucleus spins. In many observations of 3I Atlas, the coma looks surprisingly smooth and symmetric. Not totally featureless, but far less patchy than you would expect if strong, localized jets were doing the heavy lifting for that course change. It is as if the object wants to show us activity, but not the ragged, uneven kind that normally accompanies a big directional shove. Then there is the timing. The key acceleration appears to have happened right around perihelion, while the object was behind the sun from our point of view. This is exactly when natural outgassing should be strongest, because solar heating peaks there. It is also exactly when our tracking is weakest, because the sun blinds our instruments. Natural and artificial stories both love this window. One says this is just where the physics is most intense. The other says this is where you would hide a maneuver if you did not want nosy primates on a small blue planet to notice. Supporters of the natural view lean hard on the diversity of comets. They remind everyone that comets have surprised us over and over again. Some fall apart without warning. Some brighten long after perihelion as buried ice wakes up. Some show bursts of activity so regular that they look planned until we map them to weird shapes and rotation states. In that light, 3I Atlas is simply the latest member of a very unruly family. Odd, yes. Unprecedented, not really. On the other side, the guided machine camp stacks the coincidences into a single picture. A trajectory that was already uncanny becomes even sharper after the conjunction window. A non-gravitational acceleration that points almost exactly along the ideal correction vector. A coma that is too tidy for the amount of thrust implied. An approach that lines up with a gravitational harbor around a gas giant, exactly where a patient, infrastructure-minded intelligence would want to park. Taken together, this stops feeling like random behavior and starts feeling like navigation. There is also the psychological weight of the conclusion. If we decide it is artificial and we are wrong, we have fooled ourselves with our own pattern hunger. Neither outcome is attractive. Astronomers are trained to prefer the risk of missing the spectacular over the risk of believing a story that is not really there. That is why the official line stays conservative, even as private conversations get more adventurous. In the end, this part of the story is not about picking a side. It is about realizing how thin the line has become between the two. 3I Atlas sits in that uncomfortable borderland where natural and artificial explanations both fit the broad strokes and differ in the fine print. The only honest position right now is that we do not know which one is true. What we do know is that if this is a guided machine, it is following a logic we can understand, using the same gravity tricks and energy sources we ourselves have started to dream about. And if it is just a comet, then nature has somehow written a path that looks disturbingly like a plan. Either way, when you watch it close in on Jupiter's territory, it is hard not to feel like you are reading a message. The open question is whether the message says comet or craft. If 3I Atlas is a machine, its strangest feature is not the precision of its orbit, it is the silence. No pings, no beacons, no obvious attempt to talk. That silence fits a very old idea that has been haunting astronomers and science fiction fans for years. The universe might behave like a dark forest. Every civilization is a camper with a small fire, terrified that if it shouts hello into the trees, something bigger and hungrier will hear it first. In a place like that, the smart move is not to announce yourself. It is to hide. In the dark forest picture, the galaxy is full of minds that know two things. First, resources are finite. Second, you can never truly know another civilization's intentions, if contact can go wrong in ways you cannot reverse. It is not a hopeful vision, but it is brutally logical, and when you look at 3I Atlas through that lens, a lot of its weirdness starts to look less weird. Think about how an anxious, cautious civilization would explore. You do not send bright, talkative ships that shout greetings across radio bands. You send scouts that resemble natural objects. They give off no clear signals beyond reflected light and a little thermal glow. Their propulsion systems are designed to blend in with comet jets or asteroid maneuvers. Their trajectories imitate the messy, long arcs of rocks thrown from forming planets. To anyone watching casually, they are just part of the debris. Now place yourself in their shoes as you approach a system like ours. You pick a path that intersects the plane of the planets. You pass Earth at a distance that lets you listen in detail, but you do not dare adjust your course in a way that would scream intention. You let your sensors quietly soak up data on our atmosphere, our radio noise, our orbital clutter. If you have done your homework in advance, you already know roughly how advanced we are from our leaked emissions. There is no need for a dramatic flyby. No need to point anything directly at us. The safest choice is to act like you do not care. Then you head for the high ground. In human history, nobody with a military budget ever ignored a mountain ridge that overlooked a valley full of activity. You build your watchtowers where the physics gives you leverage. Jupiter's hill radius is that ridge. Park your hardware there, and you can watch the whole inner solar system while staying wrapped in radiation and magnetism that hides your presence. You see rockets rise from Earth. You see nuclear flashes in the upper atmosphere. You see the warm glow of cities on the night side. All of that without ever rolling the dice on direct contact. Under that strategy, the silence during the Earth pass is not an insult. It is a safety rule. Do not aim your instruments in ways that would cause dramatic changes in brightness or heat. Do not alter your path in any way that might give away that you are steering. Observe, record, move on. Save the active deployment for a place where the locals are unlikely to visit anytime soon. That place, again, is Jupiter's gravity bubble. We see the same logic in our own behavior when we are nervous. Militaries use aircraft that look from a distance like civilian planes. Submarines hide under layers of noisy ocean water. Reconnaissance satellites follow orbits that seem ordinary unless you know exactly what they are pointed at. The more you fear being seen by someone more powerful, the more you lean into camouflage and ambiguity. If the dark forest idea describes the galaxy, then 3i Atlas looks exactly like what a cautious hunter would send into the woods. There is another unsettling detail in that metaphor. In a dark forest, you are not just hiding from predators. You are also hiding from peers, from other hunters, from beings just as nervous as you are. That makes the safest universal rule very simple. Never be the loudest thing in the clearing. Our radar pulses bounce off asteroids and ring like bells. Our satellites glitter in orbit. If you are watching from Jupiter, you do not need us to speak directly to you to know we are here. We have already lit the fire, so what would count as cautious behavior for them now? One option is to maintain pure observation mode. Leave a network of sentinels in Jupiter's neighborhood. Let them blend into the asteroid population, and never send a return message at all. Another option is to wait. In the dark forest view, you do nothing until the locals either become obviously peaceful or obviously dangerous. That might mean watching for centuries as we grow into a spacefaring species, tracking how we handle power and risk. War in orbit might look very different from peace in orbit when seen from a distant watch post. This logic of hiding is hard to accept because it moves us out of the center of the story. We like to imagine that any alien technology entering our system would care deeply about us, either as threats or as friends. A dark forest mindset says we are neither right now. We are a data source, a file being updated in some remote archive, important enough to study, not important enough to risk talking to. 3i Atlas, in that picture, is not a herald. It is a survey drone that stayed in character even when it skimmed past the one world in the system that wonders about it. If that is the game being played, then our role changes. We are not being invited to first contact. We are stumbling across the hunting blind that someone else built. The question is whether we choose to keep pretending the blind is a bush or whether we admit that it looks designed and start planning accordingly. Because in a dark forest, learning that someone else is there is only the first step. The real challenge is deciding what to do with that knowledge without lighting up the whole clearing. While 3i Atlas is threading its way toward Jupiter, something just as strange is happening on our side of the story. Our own machines are quietly learning how to see the sky in ways no human ever could. This is not just better telescopes or bigger mirrors. It is an entirely new kind of vision. A layer of artificial intelligence that sits between the universe and our eyes, catching patterns, flashes, and motions that would have slipped through our fingers before. For most of history, astronomy was a human sport. Someone pointed a telescope, stared, sketched, and compared notes. Even when digital cameras took over, people still combed through images by hand, marking the odd speck that moved or the star that brightened. That world is gone. Modern survey telescopes produce more data in one night than a team of humans could analyze in a lifetime. You cannot scroll through it. You cannot even see most of it. You have to ask machines to tell you what matters. These survey instruments work like cosmic scanners. The Vera Rubin Observatory in Chile will soon sweep the entire visible sky again and again, capturing it in slices every few nights. Space missions like Euclid and the Nancy Grace Roman Telescope will map huge regions from orbit, building three-dimensional pictures of the universe. Every exposure contains millions of light sources. Some flicker, some move. Some appear once and never again. Somewhere inside that chaos might be something like 3i Atlas, or something even stranger, hiding just at the edge of detectability. This is where artificial intelligence steps in. Pattern recognition algorithms sift through the flood of pixels, looking for changes that match no known catalog object, a dot that jumps between frames in a way that suggests motion, a star that brightens and dims in a pattern that does not fit normal flares, a tiny lensing effect where the light from a background star bends for a fraction of a second, hinting at a small mass passing in front. The machine does not get bored. It does not blink. It just flags anomalies. Thousands of them. Most of those anomalies are mundane, satellites flaring as they catch the Sunday cosmic rays striking the detector, known asteroids wandering through the field. But a stubborn remainder refuses to fit tidy boxes, fast movers with awkward velocities that do not match simple orbits, transients that appear too bright and fade too fast to be common supernovae, microflares from patches of sky that seem empty on every other image. Each one earns a note in a database and a round of nervous checking. The uncomfortable truth is that we already have more weird detections than we know what to do with. Researchers are cautious. Careers depend on not crying wolf. If an artificial intelligence flags something truly outrageous, like an object that seems to cross the sky at a fraction of the speed of light, or a lensing signal that implies a tiny but incredibly dense body, the first instinct is not to publish. It is to doubt the software, the calibration, the instrument. People rerun the pipeline. They build new filters. They quietly ask colleagues for second opinions, all before a single word reaches the public. Now place 3i Atlas into this environment. As it approaches Jupiter, the number of instruments capable of watching it increases, and their brains get sharper. Ground-based surveys track its position night after night. Space-based observatories peek at its coma in wavelengths inaccessible from Earth. Artificial intelligence systems watch for any unusual change in brightness, motion, or shape. If it fragments, they will see the pieces. If those pieces behave oddly, the machines will be the first to notice. There is a strange symmetry here. On one side, we may have a messenger from another star system, built by minds that learned long ago how to hide in natural processes. On the other, we have our own fledgling machine minds, trained to see past noise and find the faintest hints of intent in data. Two learning curves crossing, their technology arriving in our system, while our technology finally becomes able to recognize that arrival for what it is. It is possible that this timing is pure coincidence. The universe is big. Our progress in computing was driven by smartphones and advertising, not by some secret interstellar schedule. Yet from the outside, from a cold, galactic point of view, it would look almost choreographed. A carrier object home in on Jupiter's gravity bubble at the same moment a young civilization finally builds the tools needed to tell the difference between a random comet and a guided machine. If there is any kind of cosmic test being run, this is exactly how it would feel from the inside. Confusing, noisy, full of hints, but no simple proofs. In the coming years, the real detectives will not be single telescopes or single scientists. They will be networks, arrays of instruments feeding oceans of data into linked artificial intelligences that learn, slowly, what normal looks like for the sky. Only once normal is understood can abnormal stand out. Only then can we say with confidence whether objects like 3i Atlas are rare or just the first ones we have managed to see clearly. And if the machines do find a pattern, if they quietly assemble a list of objects whose motions and signatures look more like plans than like rocks, the first sign will not be a dramatic announcement or a flashing headline. It will be a series of quiet papers, a handful of curves that do not fit, a growing stack of anomalies that force us to admit that something about our mental picture of the solar system is incomplete. The moment of realization might come not from a telescope in a desert, but from lines of code running in a server room, drawing a conclusion we taught it how to reach. At that point, 3i Atlas will no longer be just a mystery object with a spooky orbit. It will be a data point in a larger pattern, one node in a network of questions. Are there more like it already sitting near Jupiter? Are there others near Saturn, Uranus, or Neptune? Have we already cataloged them as minor moons or dark asteroids without noticing the signs of guidance? The machines that learn to see the sky will be the ones to tell us. The real question is whether we will listen when they say the universe looks different than we thought. Every orbit is a story with a last act. For 3I Atlas, that act plays out in the deep outskirts of Jupiter's domain, where the gentle pull of the sun and the brute grip of the gas giant balance and blur. Right now, from our vantage point, we are living in the long middle chapters. The object is inbound, the calculations are tightening, and all the arguments about Comet versus craft are still mostly theoretical. That changes when it reaches the hill radius. At that point, the sky will either shrug or do something that forces us to rewrite the script. So what should we actually expect to see as it arrives at Jupiter's gravity bubble? The simplest outcome is the least dramatic. 3I Atlas could behave like a tired interstellar comet that has finally had enough. It crosses the boundary. Its nucleus cracks under thermal stress and tidal forces. Chunks drift away, spreading into a diffuse cloud that wraps a faint halo around Jupiter's orbit. Our instruments log a rise in dust. The fragments follow orbits that are messy but explainable. Solar radiation and Jupiter's pull slowly smear them out over years. Weird? Yes. Terrifying? No. The story ends as a footnote in dusty comet catalogs. Another natural scenario is quiet capture. The object slides into the hill radius, loses a bit of speed to Jupiter's gravity, and settles into a long, loose orbit that loops far from the planet but remains bound. Over time, perturbations from other planets and the sun reshape that path. After a few million years, the original identity of 3I Atlas is gone. It is just one more irregular moon or distant Trojan companion, part of the planet's extended family. On human timescales, nothing much happens. The drama lives only in equations. If that is all we see, the artificial hypothesis does not vanish, but it becomes much harder to argue for. Strange is not enough. You need signatures that do not fit normal physics, and drifting rubble does not qualify. The guided machine story demands more. Small, specific moves that cannot be written off as chaos or chance. If 3I Atlas is a carrier, the hill radius encounter is when those moves must appear. That is the deployment window, the moment when a simple rock transforms into a network. From our side, we will track this with a mix of old and new tools. Radio telescopes will listen for any unusual bursts as the object and Jupiter's magnetosphere interact. Optical surveys will watch for sudden changes in brightness or structure. Space-based telescopes will stare in infrared, looking for warm spots and fresh fragments. Artificial intelligence systems will chew through the stream of measurements, searching for patterns in the motions of any debris. The good news is that we know where to look and when. The bad news is that the signals we care about might be faint by design. In a natural fragmentation, pieces break off and drift apart in ways that reflect the geometry of the breakup. Some lag behind. Some race ahead. Their orbits spread slowly, influenced by sunlight and gravity. In a deployment, you would expect something else. Fragments that move with purpose. Relative velocities that are small but tuned, placing pieces into very specific paths. Some might break just enough to slip into orbits near L1 or L2. Others might start to climb above or below the orbital plane in coordinated arcs. To see that, we will need high-precision tracking of objects that may be only tens or hundreds of meters across. There is also the question of energy. If any fragment uses onboard propulsion, even briefly, it might release heat in ways that stand out. A short, sharp brightening in infrared wavelengths at the moment of separation. A flash not easily explained by the slow grinding of ice and rock. We saw nothing like that during the Earth pass, but the physics near Jupiter is different. There is more gravity to work with, more potential energy to trade, and a stronger reason to spend precious propellant. If this is a mission, this is where you use the fuel. Of course, a clever design would try very hard not to give us that satisfaction. If you were building a carrier to deploy sentinels invisibly, you would time your maneuvers to coincide with natural stresses. Let the breakup begin under the strain of Jupiter's pull. Then hide any deliberate pushes inside the mess. Use cold gas thrusters that barely warm the surface. Keep the burns small, closer to gentle taps than roaring rockets. From afar, every move would look like the aftermath of a natural disintegration, even if the final positions of the fragments are anything but random. This is why the next phase feels like a countdown, but not to a single spectacular event. It is a countdown to a fork in our understanding. As 3I Atlas enters the hill radius, every small choice it seems to make will tilt the scales. Does it stay roughly intact and exit on a predictable path? Does it shatter into a debris trail that behaves like every other disrupted comet we know? Or do we see a pattern of motions and placements so suspiciously tidy that even the most cautious scientist has to admit that nature would be working very, very hard to keep up the illusion? There is a real possibility that we will miss the truth the first time around. Our instruments might not be quite sensitive enough. Our sky coverage might have gaps. A key sequence of motions might unfold while Jupiter is inconveniently placed relative to Earth. Years later, better data might reveal that we watched a deployment and filed it under ordinary behavior. That is another reason this moment matters. It is not just about what 3I Atlas does. It is about how seriously we choose to look. If we do commit, if observatories and agencies treat this as more than a curiosity, we have a chance at something unprecedented. A before and after picture of a possible interstellar machine integrating itself into a planetary gravity well. A test of Sentinel theory playing out in real time. Either we will confirm that even the strangest trajectories can be chalked up to ice and chance, or we will catch the universe doing something we have only ever imagined in fiction. Both outcomes change us. One, by deepening our respect for the wild creativity of natural physics. The other, by forcing us to admit that we are not the only intelligence writing stories in this sky. Let us accept, just for a moment, the uncomfortable possibility we have been circling. Imagine that 3I Atlas really is a guided machine. Imagine that by the time it finishes with Jupiter, there will be quiet hardware sitting in that gravity bubble, watching us for as long as our species exists. What then? What does a young civilization do with the knowledge that there may already be eyes in the dark, taking notes while we argue about whether they are real? The first step is the least dramatic and the hardest. We do not panic. We do not turn this into a story about impending invasion or instant doom. A Sentinel network is not an armada. It is infrastructure. If someone wanted to smash Earth, they would not need to park tiny machines around Jupiter for decades first. A watchtower means interest, not immediate danger. That gives us something priceless in cosmic terms. Time to think, to prepare, to grow up a little before we decide how to respond. The second step is to treat this as a scientific problem, rather than a horror movie twist. That means more data, not more speculation. We can design dedicated campaigns to track 3I Atlas as it enters Jupiter's hill radius. We can ask deep space missions already in the outer solar system to turn their eyes and instruments toward the region when they can. We can propose new probes that orbit Jupiter with an explicit goal of mapping small objects in its gravity bubble with ruthless precision. Even a null result would teach us something about how well we can search our own backyard. At the same time, we need to be honest about our blind spots. Parts of Jupiter's environment are almost invisible from Earth. We rely on patched-together observations, brief flybys, and models. If we are serious about answering the question of artificial infrastructure, we have to treat the Jovian system the way we treat Mars or the Moon, as a long-term target for orbital campaigns and patient mapping. That is true whether 3I Atlas turns out to be a machine or just the comet that finally made us notice how little we actually see. There is also a political challenge. Right now, an odd interstellar object is mostly the domain of specialists and enthusiasts. It shows up in a few headlines and then sinks back into technical talks and preprint archives. If we do see something at Jupiter that breaks the natural story, that cannot stay a niche topic, we will need institutions that can talk about it honestly without defaulting to secrecy or spectacle. That might mean international panels that include astronomers, ethicists, and yes, people who understand how societies respond to big, unsettling truths. We have already built a kind of rehearsal for this in planetary defense. When a new near-Earth asteroid is found, observatories share data openly. Orbits are refined by many teams. Risk scales are public. The entire process is designed to make sure no single agency controls the narrative. We could build something similar for interstellar objects and possible technosignatures. A standing network that collects data, cross-checks it, and reports findings in clear language, even when the answer is, we are not sure yet. On a deeper level, the existence of a watcher network would force us to rethink what it means to be alone. For generations, the search for extraterrestrial intelligence has imagined a moment of contact, a signal, a message, a clear before and after. The Sentinel picture is different. It says contact may already have happened, but in a one-sided way. They have seen us. We have only just noticed the possibility that they are there. That is not a dramatic first handshake. It is more like realizing halfway through your life that there has been a camera on the wall the whole time. That realization cuts both ways. It can feel invasive, like a loss of cosmic privacy we never really had. It can also feel strangely reassuring. If someone has been watching us quietly, and we are still here, then at least so far we have not tripped whatever thresholds would trigger intervention. Maybe the dark forest is not as lethal as the bleakest stories suggest. Maybe the default strategy is not shoot first, but watch for a very long time and only act when there is no other choice. The practical question is whether we ever try to speak back. Should we aim a narrow beam toward Jupiter's Hill radius and whisper a careful hello? Should we encode a message on one of our own probes and send it to share the same space? Or should we remain as quiet as possible, focusing on listening and understanding before we take the risk of drawing direct attention? There is no consensus on this, and there will not be one for a long time. Any decision to actively respond would be the closest thing humanity has to a global choice, one that affects every future generation. For now, a more grounded path is open to us. We can use the possibility of being watched as a mirror. If there really are instruments sitting out near Jupiter, logging our emissions and tracking our rockets, what story are we telling them? A species that burns its own nest and cannot cooperate beyond its borders? Or a species that slowly learns to manage a planet, share power, and build structures in space without dropping debris on its own head? Whatever 3i Atlas turns out to be, we are still writing the part of the story we can control. In that sense, the most important reaction might be philosophical rather than technical. We stop assuming the universe is empty until proven otherwise. We stop imagining that intelligence begins and ends with us. We start planning our future as if we live in a neighborhood where someone might already be taking notes on how we behave. That does not mean paranoia. It means responsibility. It means understanding that our broadcasts, our engineering choices, and even our wars are not happening in a vacuum. They are part of a record. So we watch 3i Atlas finish its long approach. We build better telescopes. We train smarter machines to read the ceaseless flicker of the sky. We argue, loudly and honestly, about what the data really says. And when the moment comes that we can no longer pretend our solar system is an untouched wilderness, we meet that moment with curiosity instead of fear. Because whether this object is just a comet on an improbable path or the courier of a sentinel network, it has already done something remarkable. It has forced us to look at our own backyard with new seriousness and to ask, maybe for the first time, and really mean it, who else might be here with us?